definitely not now. So, with no further ado, here's Chris, and he's going to be talking about, well, you can do that yourself. Come on.
Yep.
Give him a hand, come on.
Well, thank you for that fantastic introduction. I actually told him not to say anything because I've got a slide where I talk about myself anyway, so just in the interest of time. And yeah, it's kind of hard for me to look up. It's such a steep room. Anyway, so thanks for choosing this session. So if you're like me, then probably most of the apps that you've been building over the years have just consisted of a single WAR file. They've had a so-called monolithic architecture. And so in that kind of app, HTTP request comes in, the app just goes off to the database, does some updates, queries some data, generates an HTML page or a JSON document. You know, really, really simple request processing. So, and for many apps that works well. The problem you have is that when you're building a large, complex application, for a bunch of reasons that I've covered in another presentation that I tweeted about earlier, that approach, that single monolithic WAR file architecture really doesn't scale. And what you need to adopt is a microservice architecture where the application consists of a collection of typically quite small services that collaborate via REST or via a messaging broker in order to fulfill requests. And the interesting thing about this architecture is that it really changes how requests are handled. Because a request typically comes into a front-end server, but instead of being handled there, actually the request gets fanned out to multiple back-end services. You know, Twitter talk about how, or Netflix rather, talk about how on average a request fans out to roughly 6 back-end services on average. Amazon talk about how a request to, say, render a product details page can actually involve hundreds of services. So the way in which you're handling requests is quite different. And what that ends up leading to is that you end up having the code in the front-end server has to be written in a concurrent style. If you're calling multiple back-end services, you can't call them sequentially, but instead you have to call them in parallel in order to minimize latency. And that's sort of really kind of the motivation for this talk, even though the technologies that I'm talking about actually have quite broad applicability. Sort of how I got interested in them was just in the context of building API gateways. So I'm talking about sort of 2 abstractions. The first are futures, specifically Scala Futures, not the sort of primitive, half-broken futures you get in JDK7, but sort of more modern future implementations in Scala, and also in some add-on libraries to Java, and also more or less what you get in Java 8 as well. They're not quite as good as Scala. And then I'm going to talk about another really interesting, absolutely fascinating abstraction that's great for dealing with processing potentially infinite asynchronous streams of data, namely Rx or reactive extension observables that are being popularized by Netflix in the form of RxJava. And I'm going to show how using these abstractions you can take your asynchronous code and write it in a very sort of simple, robust, and scalable fashion. So before I get into that, a little bit about me. So I actually got my start way back in the late 80s building Lisp systems, compilers, all the way up to IDEs and frameworks and so on. And that sort of colored, kind of how I sort of look at software. It's hard to get Lisp out of your system. Eventually I ended up programming in Java, and then 8 years ago wrote the book Pojos in Action, which is all about how to build apps with Spring and Hibernate, which back then were these pretty radical technologies that were revolutionizing enterprise Java development. And then in more recent years, I got into cloud computing. I created a startup called Cloud Foundry that was eventually acquired by SpringSource shortly before SpringSource was acquired by VMware. And I should say that this is not drawn to scale in terms of market cap, because otherwise I'd be fabulously wealthy now. I really would. No, I mean, Cloud Foundry was much more of a plankton than a fish, actually. So So I actually left the whole VMware Pivotal world back in August. And so one of the things I'm working on is some buzzword compliant startup. So it's social, big data, machine learning, blah, blah, blah kind of startup. And also doing some consulting, helping people kind of build and develop and deploy applications using modern technologies, the cloud, microservices, polyglot, NoSQL, and so on. So that's me. So here's the agenda. So first I'm going to sort of dive more into the motivations for concurrency, and then I'm going to look at futures in both sort of Java limitations, how you can do better in Scala. And then I'm going to finish up by talking about reactive extensions, so-called Rx Observables, and how you can do some really, really interesting things with them. Okay, so, why do we need concurrency in this sort of a front-end server that I mentioned? So let's imagine that you're building an online store. You're creating the next Amazon.com, for example. One common feature of an online store is you're going to have a product details page. And if you go look at the Amazon version of product details, it displays a tremendous amount of information. So, you look at the page from my book, it's not just, picture of the cover, the title, and so on. There's reviews, there's shipping information, like how long it would take to ship to you, 1 day, 2 day shipping. There's also recommendations. You scroll down, there's some more product info, there's the sales ranking, there's more reviews, and then if you keep going, you see related books, there's also a forum, there's the viewing history, and actually so it goes on. So there's a tremendous amount of data gets packed onto a conceptually simple page. And not only does that work in a web browser, but it also is supported on mobile clients as well. There's like iPhone client, also Android. So you end up, eventually, if you go along this path, you're going to build an application that looks something like this. So on the front end, you've got various different types of clients, desktop browser, mobile browser, as well as multiple kinds of native client as well. iPhone, Android, maybe Windows Mobile as well. And then the back end, instead of consisting of a single large monolithic WAR file, you've actually got a collection of services. Each one's responsible for some functional area of the application. So you can imagine you've got a product info service that's got basic product info. You've got a recommendation service that manages recommendations. And then you might have a review service, and so it goes on. And you could imagine having a sales ranking service, a forum service, on and on and on and on. And then between the front end and the back end, you'd have some kind of front-end server that's either a traditional web app, so it's serving up HTML, say, to desktop clients in a mobile browser, but it would also function as an API gateway, a proxy server, so to speak, so serving up JSON in response to requests from a native mobile client or possibly a HTML5 JavaScript client running in a browser. So we've got quite an interesting architecture at this point. So then the question is, well, in this architecture, how does the client, the browser or the native client, get the product details in order to display that page that I showed earlier? How does it interact with each one of these back-end services? So one option, of course, is that the client could make multiple requests to each individual service, though they're sort of routed via this front-end server for a bunch of reasons I've covered elsewhere. It gets the product info, so that request comes into the front-end server, gets proxied to the product info service, and then it can get recommendations, that's routed to the recommendation service, and so on and so forth. So that's definitely one approach. So all of this data is being aggregated on the client. The trouble is with this approach is that it requires really good network performance. There's a lot of packets going back and forth, and maybe things need to be done sequentially, so perhaps there's latency issues involved as well. So, and of course, mobile networks, despite, they're still not great. So this probably wouldn't work so well over a mobile network. Maybe it would work well over, Wi-Fi or Ethernet. So the other option, of course, is for the browser or the client to make a single request into the front-end server, which then does the fan-out. And that's kind of nice because it's just one round trip over the wide area network, so that's really, really good for mobile clients. And then over the LAN, there's lots of requests going out to the ProductinfoService recommendation service and so on. And then once all of that data has been gathered by the front-end server, it can then spit out HTML or it could spit out JSON depending on what the client needs. And in a lot of cases, this sort of server-side aggregation approach is the preferred one. So if we go down this route, that sort of then leads to another question is, well, how does the front-end server call all of these back-end services? So it could do it sequentially. You know, it calls ProductinfoService, waits for the response to come back, calls recommendation service, waits for the response, and so on. Downside, of course, there is that you get a very long, high response time. It's the sum of the response time of all of the back-end services. So that doesn't really scale very well if you're calling a lot of back-end services. And interestingly, if you think about a lot of the code we've been writing that involves hitting a database, which is kind of relatively a high latency service, this is exactly what we do, but it sort of doesn't really impact us quite as much as making remote calls to multiple potentially overloaded services. So the other approach, of course, is to do it in parallel. So when we do this, a request comes in, and we just call all of those back-end services in parallel, gather up the data from them, and then return it back to the client. And that gives us a much better response time, basically the maximum response time of any of those back-end services. And so that's sort of the motivation. Or if we need to do things in parallel, then we need to write some kind of concurrent code. And since what we're doing is actually calling RESTful services, that means that the front-end server actually has to have some kind of concurrent REST client running within it. And of course there's a bunch of options. We could just use thread pools, we could use we could just put each each piece of call to the code that does an HTTP request, submit that to an executor service, and have it executed concurrently. And that thread-based approach is sort of simple, but it's not very scalable in IO-bound code like this, because all of these threads will be sitting around blocked, waiting for the response to come back, and that's just taking up memory. And a much better approach, of course, is to use an NIO-based client that's just effectively a single threaded event loop that's just going to notify you when the request is completed. The downside of that, of course, is that the code ends up being a lot more complex, even though it's a lot more scalable. And then in either case, we have to handle partial failures, but I've sort of covered that in another talk, so you could go look that up online. So the sort of so hence we've gone all through this path, and we've now decided, well, we've got to write a concurrent REST client, and we've got a couple of different approaches, and so let's sort of dig into that in a little bit more detail. So, I found that a really great abstraction for writing concurrent code, rather than dealing with thread pools or callbacks explicitly, is to use futures, which of course have been in Java for quite a long time. And they've actually been part of programming languages since about the early 70s. So just a quick refresher on what a future is. So you can think of a future as a sort of a little box that eventually holds the result of a concurrent computation. So you can imagine running on some thread a client, and that initiates an asynchronous operation, perhaps in a thread pool or in using some event-driven mechanism. And when it does that, a future is created. So a future is this little box that's just sitting there waiting to receive the result. And then when the asynchronous operation completes, it puts the outcome, either the value or an exception, into the future, and then the client can retrieve it. And that's pretty much it at a basic level. And, it's simple, but it actually has a number of benefits. It's a very simple way for two concurrent activities to communicate easily. We don't actually have to worry about concurrency or locking or, any of the hard parts of Java concurrency. If we're using futures, that's all abstracted away from us. And what's more is the client doesn't really know how that asynchronous operation is implemented. It doesn't know whether it's using thread pools. It doesn't know that it's using an event-driven approach. That's hidden away. And then what's more, in this particular sort of scenario, it makes it very straightforward to implement scatter-gather type operations. So you can initiate a whole bunch of asynchronous operations, get a future back from each one. So you call the recommendation service, you get a future, you call the product info service, you get a future, you call the review service, get a third future for that. And then you just wait for those futures to be filled up with a value, and you're done. And so it's a nice, simple abstraction that's really useful in this particular context. So we look more at the design of the front-end server. So we're going to have a product details controller that handles the HTTP request. It's going to call down into the product details service, which is then going to call each one of those back-end services via these stubs or proxies that in this particular case is going to use a Spring REST template. So that's just wrapping the HTTP APIs. So that's the design of our code, so you want to keep that in your mind throughout this presentation. So, I'm using Scala, but it's just sort of pretty readable. So you can imagine the product info service has this API, takes a product ID, and then it returns a future that will contain product information about the product. And in a Spring application, we can implement it using code like this. So we're using the add async annotation to tell Spring when this method is invoked, go off and execute it within a thread pool. So we don't actually have to explicitly submit a callable to a thread pool ourselves. Spring is taking care of that. And then the function that this getProductInfo method, it invokes the Spring REST template to do the HTTP GET, and then wraps the result up in an async result that's really just a concrete, an implementation of the future interface. So that's just how we can call something asynchronously. Pretty basic stuff. So if we move up a level and look at the product details service that's aggregating all of the futures together, it calls product info service, gets a future, calls recommendation service and the review services and gets another future. And then, so it's now at this point, it's initiated 3 asynchronous operations, and then it has to wait for the values to each one of those futures to be fulfilled with a value. And then this is where it gets interesting, because the only API that you have in Java is just to call get, which with a timeout value, so we just sort of wait for 300 milliseconds for product info to return, or to complete rather, and that gives us the value, and we do the same for the recommendation service and review service, and then we build up a product details object that aggregates the 3 values. So on the one hand, that looks kind of straightforward. But there's some interesting problems with that I'll get to in a couple of slides. And then the product controller just calls the product details service, and because of the @response body, that annotation says take the object that's returned by the controller method, the product details object, and serialize it to JSON or XML, whatever the client's expecting. So, it looks kind of simple, but there's like one big problem with this is that when you call get on a future, that call blocks. And this is a web application, so that's actually going to tie up a Tomcat or Jetty execution thread. So in other words, we're going to be blocked in the web tier until the back-end services have returned data or we're timed out. And because sort of execution threads are somewhat, they're somewhat of a precious resource, that's really going to limit the scalability of our code. And so that is sort of highlighting a big problem with with a Java Future API is that it's actually blocking. You can actually poll, but that at the end of the day, that's basically the same as blocking. And then there's actually more subtle problems with Java Futures. And if you go read this posting by Netflix on their tech blog, they actually dive into that in a little bit more detail. I'd encourage everyone to do that. So what can you do about it? Well, the real solution actually is to use a better future implementation, one that actually supports callbacks. So rather than you having to ask the future, are you done yet? Instead, the future tells you via a callback that it's completed either successfully with a value or it's failed with an exception. So in this example, I've got an async square function that takes an integer and then in an asynchronous fashion, it eventually returns a future that is the square. It returns a future that eventually gets fulfilled with the square of that integer. So f in this case is a future, a Scala Future. And then we can attach callbacks to it. So that we've got an onSuccess callback that's invoked when the future is completed successfully. And we've got an onFailure callback that gets invoked if the future contains an exception. So in this case, it will print, 625 if I've done my math right. Otherwise, it's going to print out exception thrown if there was some kind of failure. And there are various, so this is Scala, which actually has the nicest future implementation, but Guava has ListenableFuture. Spring 4 has ListenableFutures as well. And then Java 8 also has completable futures that all of them let you attach callbacks. So, on the one hand, this is not bad, because we could attach callbacks, so we get 3 futures, we could attach callbacks to each one, and then we could use a countdown latch to keep track of whether we've got results from all 3 futures yet. But the problem you run into is that the callback-based code, if you've ever written any JavaScript, gets very messy quite quickly. You end up with callback hell if there's any level of complexity. So, but what's nice is that Scala actually takes the concept of futures sort of another step further and actually has a much richer future API that actually lets you compose futures in very nice functional ways. So here's a great example of that. So, in this case, one example is the zip function. And so in this case, we're calling async square with 5 and 7. And then we're calling zip. And what zip does, it takes 2 futures and then returns a third future whose value is a tuple of the values from the input futures. So it actually, in this case, the value of fzip is 25,49. And what it does in one simple sort of functional way, it's actually doing a gather. It's actually, under the covers, it's attaching callbacks to those 2 futures, and when they complete, it's pushing the combined value into the third future. And then there's also future.sequence that takes a list of futures and turns it into a future and gives you back a future whose value will eventually be a list of the values out of those input futures. So you've got very simple functional ways of basically combining multiple futures into a single future. And this is all done in an asynchronous fashion. So if we look at what zip is doing, it takes f1 and f2, creates a third future, which you get immediately, and then it attaches callbacks to f1 and f2, such that when those futures complete, the outcome of each one is then combined and put into f3. So it's sort of doing what you would do via callbacks, but that's all taken care of for you, which is really, really helpful. And then there's also Scala Futures also implement a map function that that returns a future immediately, and that future will be fulfilled but with the value that's obtained by applying a function to the eventual value of the input future. So async plus 4 and 5 is eventually going to give you 9, and then the map function, map is then going to multiply that value by 3. So eventually you're going to get 27 out of this. And once again, that's all being done in an asynchronous fashion. So you can just sort of chain zips and maps and other functions that combine futures together to asynchronously transform values in a functional style. And there's also flat map, which lets you chain together asynchronous operations. So in this example, we're calling async plus 5 and 8, which will give you back a future that eventually will contain 13. And then when it completes, it kind of behaves like map. So it then passes that eventual value to another function, except that function actually returns yet another future. So we're calling async square with 13, which eventually gives us back a future that will eventually contain 169. And so this lets us chain together asynchronous operations. And you end up being able to write code that's incredibly simple. And if you didn't have this kind of composability, you would actually have to write very tangled callback-based code, which would be a huge mess. So these days, the term monad is sort of popular, and turns out that Scala Futures are in fact monads because they implement flat map and so on. And what that actually means is that, you can write code like this, that's on this slide, but because they're monads, you can actually rewrite this using Scala's for comprehension. And you end up with very simple code that looks almost sort of sequential in nature, but it's really concurrent underneath. And that's actually quite nice. So here we're calling async plus and async square, zipping the results together to give you a tuple, which is then being destructured into A and B, and then we're taking A and B and passing those to async plus, that's giving C, and then multiplying the value C by 2. And that's all happening, even though it looks sequential, that's all happening asynchronously, and it gives you a future that you can then attach callbacks to and get the result of. So let's go, so we've kind of looked at Scala Futures, so let's just go look at how we can apply those to the product details service. So the first thing, here's product info rewritten to use Scala Futures. And the first thing you notice is that it really hasn't changed too much, except that we've got rid of the @async annotation, which was being used to execute the call to REST template within a thread, within an executor service, and instead we're actually using the future function to do that for us. So under the covers, it's actually still being executed in a thread pool. So we haven't actually changed what's going on at this level. We're just doing it the Scala Future way. So no big deal there. But what's really exciting is what's happened with the product details service. So rather than blocking by calling get on Java Futures, it's now rewritten using this nice functional style. So we zip together the 3 futures that we get, and then use the for comprehension to take those values and create a product details object. So we're actually gathering up all of that data, combining it together to give you a result value without blocking in any form or fashion. So that's a whole lot nicer. So we're not tying up a thread there. And then the final piece of the puzzle here is that, well, if we don't want to block at the servlet level, we need to use the servlet 3.0 async API, which in the Spring framework is sort of encapsulated by using controller methods that return a deferred result, which actually basically behaves like a future. So the controller method returns a deferred result, and then the controller code at some point has to push a value into it. So it's another container of a value that appears eventually. So in this code, we actually call product details. So we get a future. We then instantiate a deferred result. And then the final bit is to attach callbacks to the future that propagate the outcome of that future into the deferred result. So in other words, if the future contains a success value, we call deferred result.setResult, just passing it in. Otherwise, if there's an exception, we call result.setErrorResult. And so the deferred future gets returned immediately, and then those callbacks, one of those callbacks will get invoked, and that will then trigger Spring's MVC to generate a response. But the neat thing here is that, this is all happening completely asynchronously using the Servlet 3.0 API. So we're not actually blocking in any way at the servlet level. But what is going on is with the backend is still using those thread pools. So in order to make that code more scalable, we need to use an event-driven REST client. So that's sort of the final piece of the puzzle here. And what's really cool is that Spring 4.0, which came out relatively recently, has an asynchronous REST template that basically behaves like the other one, the old REST template, except that it's got an asynchronous API and uses the Apache HTTP components, async HTTP client. So that's all using NIO. So we've got this nice high-level wrapper to the NIO mechanism. And its methods return a listenable future that's a Spring-specific sort of enhanced future. So it's a JDK7 future that lets you attach callbacks to it. So it's kind of the problem in the Java world. There's like all these kind of random future implementations. Hopefully JDK8 will solve that problem. So if we then go back to ProductinfoService, here it's been rewritten to use the AsyncRestTemplate. So we call get4entity that gives you back a listenable future. And then we have to convert that into a Scala future. And the next slide shows the code that does that. So, and also we're doing a map over it. So two Scala future gives you back a Scala future, and then we're using map to actually get the body, get the actual product info object out of the value that gets returned by get4entity, because there's sort of like metadata in there as well. And the way we end up converting a listenable future to a Scala future is, first off, we create a promise, which is sort of the Scala way of instantiating a future. And then we attach callbacks to that listenable future, which just propagates the outcome of that listenable future into the Scala future by calling p.success, p.failure. And then we finally return the actual future that's been created by that promise. Once again, that's all happening asynchronously. So if we do that, then that means that it's sort of every level, we're not blocking, we're not using threads, and we've sort of got this wonderfully scalable application. So, all 10 users of our app will be really happy. It's interesting, I kind of think that sort of the whole scalability thing in a lot of cases is sort of overblown, but it's fashionable to be scalable and non-blocking these days. But there is, so you've sort of seen that we've got these nice functional abstractions for writing non-blocking, event-driven code. So we've got this. It is quite nice. But there are some downsides. So namely that it can actually be really, really hard to figure out what your code is doing if it's behaving badly. And one reason is that in this style of code, operations are initiated in one thread, but then they fail in another. And so if they're failing in this sort of worker thread, you get a very small stack trace that often doesn't tell you anything useful. And the whole context for that operation, which was over here in the other thread, is completely lost. And it's like it can be a little tricky figuring out what's going on. Especially in JavaScript, which, weakly typed, hideous language. But it is better in Java, but this is sort of one of the inherent sort of trade-offs that you have to make, right? If you want scalability, you write it in a non-blocking style, so you tend to have to give up on debuggability and understandability as well. And then a second problem that I've run into repeatedly is futures make it very easy to forget to handle errors. So, a future will contain either a success value or a failure value, an exception. And what I've noticed is it's very common, at least for me, to write the code that handles the happy path. So I'll write some future.map or for each and do something, which does something only in the success case and completely ignores the failure case. And it just the error just disappears at that point. It's like having a catch block, an empty catch block. And I got bitten by this repeatedly, and you just have to train yourself to, you have to remember that a future might contain a failure, and to always, at a minimum, log it somewhere. So that's something to remember. All right, so that's futures. So I sort of want to change gears now and finish up by talking about reactive extensions, which is another concurrency abstraction that's being sort of popularized by Netflix right now. So what was interesting is that Netflix actually started using reactive extensions because they wanted a future implementation that didn't have any of the drawbacks of Java futures, but they wanted a sort of cross-language, cross-JVM language implementation that actually wasn't, say, tied to Scala. So they ended up picking reactive extensions, which are actually way more powerful than futures. And I'm sort of going to illustrate that with sort of a really interesting example. So let's imagine, you're working in financial services and you've got a stream of trades, maybe on being published to a message broker, and you need to calculate the 15-minute rolling average price of each stock. And so the question is, well, what abstractions are there to make solving this problem easy? So, we've looked at futures. Futures can deal with lists of things, but they're not applicable to infinite streams. Like, the whole list has to be instantiated in its entirety before it can be put into a future. And so, futures just don't help with that. And previously, and really the main abstraction that you could use for dealing with stream processing problems was typically a combination of a pipes and filters architecture. So you got message channels connected by filters that can apply functions and filter messages or route them or so on, along with complex event processing engines like Esper. And in fact, those are not, you've got Spring integration plus Esper, you can sort of do quite good things. But on the other hand, they tend to sort of require an external DSL. They're not really tightly integrated in with the language. They tend to be sort of enterprisey, heavyweight, statically defined, and so on. And sort of have a totally different feel to what I'm going to talk about next. So, which are reactive extensions. Now, I'm sort of afraid to say the word Microsoft because sort of Patrick earlier mentioned the word Microsoft and his microphone died. So, but I've said it twice now, and it's been okay. So this was a library created at Microsoft. And it was really to take LINQ, which was this database access technology, and apply it to asynchronous event-based programming. And it's sort of, to me, it was off in Microsoft land. I was vaguely aware of it, and then it was Microsoft and .NET, so sort of who cares, right? But what was interesting is that then Netflix took the ideas from Rx.net and actually re-implemented them in Java. So we've now got RxJava. So if you go to github.com Rx or github.com Netflix RxJava, there's this super cool Java library that's implementing reactive extensions. And as I mentioned a minute ago, the reason they did this is that they wanted an implementation of futures that were really powerful, kind of like Scalas, but weren't actually tied to sort of Scala frameworks and so on. And we've got this library that's now works for Java, but it also has adapters for Scala and Groovy and Clojure and so on. And it's actually really, really cool. So, the essence of it is there's two abstractions. One, there's an observable. That represents the stream of events. And then you can subscribe, an observer can subscribe to it. And the observer notifies the observable. So every time a new item is available, it calls on next. If the end of that stream has been encountered, it calls on completed. And if there was some error, it calls on error. And then the only other thing is when you subscribe, you get back a subscription that you can use to unsubscribe, and that is basically it. It's it's like two classes basically. Really, really simple. And, you can kind of compare it to the observer pattern. It basically is the observer pattern, except that it actually adds on completed on error, because effectively an observer only has on next. It's kind of like an iterator, except that it's push rather than pull. And it's kind of like a future, except that it represents a stream of multiple values. You can think of an observable that has 0 or 1 values as a future. But here it actually represents an infinite, potentially infinite stream. And you might be wondering, well, so what's the big deal? But it's actually, the core abstractions are really simple, but there's actually quite a rich interface, and you can do some really interesting things with it. So here's a simple example. So one item is an observable that just contains the long value -1. So if anyone subscribes to it, on next will be called with -1, and then on completed will be called immediately. So that's really simple. Here's something a little bit more interesting. Here's an observable that emits a value every 10 seconds. So after 10, you create one, and after 10 seconds it will emit the value 0, 10 seconds later 1, and then 2, and so on. And then we can combine them together. So now we actually have an observable that emits -1 immediately, then it emits 0, then it emits 1. And we can subscribe to that. And so on next is just going to print out 0 or -1, 0, 1. And then later on we can subscribe. So that's kind of interesting. Got support for some time-based things. And if so another more general purpose way of creating observables is by using the create function, and what a create method. And what that does, it actually takes a function that's invoked whenever an observer subscribes to that observable, and actually gets past the observer. And then and it's meant to do two things. One, it actually returns a subscription object that's used for unsubscribing at the end. And then the body of that function is meant to arrange to call on next, on completed, or on error. So you can imagine if we were creating an observable for a AMQP message queue, that function would actually subscribe to the AMQ message queue, and every time a message arrived, it would call on next, and then the subscription that you return at the end would unsubscribe. So here's an example of doing that. So I was writing some code that used DynamoDB. And when you create a table, creating a table in DynamoDB actually takes a while. So you end up having to poll to see what the status of the table is. So get table status actually calls describe table. On a DynamoDB client, gives you back a future, and then I wanted to turn that future into an observable. And basically, I attach callbacks to that future that then pushes the value into the observable. So if the future contains a successful value, I call onNext and onCompleted. So that just gives me back an observable containing the status of that table. And if there was a failure, if it didn't find it, it just says that the table's not found, and if there's an error, it calls onError. So, nice simple example of how you can take a future, turn it into an observable. But then we can do an interesting thing. We've got that ticker that's a sequence of integers every 10, or longs every 10 seconds. We can do flat map with it, and that actually polls the status of that DynamoDB table every 10 seconds and gives us back the stream of table statuses. And so in just very few lines of code, we're just sort of polling and getting a stream of status values back, which I thought was pretty slick. And if you look at the API, there's all the usual Scala collection methods as well, including map and filter and take and drop and so on. So they kind of look like collections, but they really are representing asynchronous streams of values. So, just to finish up, I want to get back to the stream of trades example. So we want to calculate an average, which really, so we've got a function that looks like this. So it takes an observable of trades, and it gives us back an observable of average prices. And actually, those two objects are kind of the same. They're just a symbol and a price. So it's kind of like, well, how do we do this? So the first thing we want to do is we want to calculate the average of price of Apple stock separately from the average price of IBM or the average price of Caterpillar. So the first thing we do is apply the groupBy operation that takes the stream and gives us back a stream of streams, one substream for each particular stock. So one for Apple, one for IBM, one for Caterpillar. So that's step one. And then we want to calculate the rolling average, so kind of over a 5-minute period. And the way to do that is using the window operation. So we're going to take the Apple stocks and then use the window operation to create a new window that's 5 minutes long, because we want to look at stocks within a 5-minute period, and create a new window every 30 seconds. So we've got this sequence. So we take a stream and we turn it into a stream of streams where each stream is a window and they're overlapping. And then we want to take each one of those windows and basically calculate the average. And the functional way of doing that is to use the foldLeft function, which takes a starting value and a binary function, and then just kind of combines the values, and so it will compute the average, and then divide by the length, and that, in this case, would say that the price of Apple, the average price of Apple in that time window is 406. Actually, that doesn't make sense. But anyway, yeah, I'm really bad at investing, actually. That's funny. It's funny, there are bugs in other slides as well, but I fixed most of the other math. But anyway, you get the idea. And then the other thing we need to do, because remember we kind of had like a stream of streams of streams, because we sort of broke them out, and then we actually need to flatten them together by merging all of those, the output, all the results of calculating the average, and so there's a flatten operator for doing that. And that gives us, so by applying flatten a couple of times, we get a single stream of average prices out. And then, and actually this is pretty much most of the code for doing that. And you can see the use of groupBy, you see the use of window, and then you can see the use of fold. for doing this calculation. And then at the bottom, there's a couple of uses of flatten. So it's kind of like a page of code, and we're actually implementing quite a, I mean, conceptually, it's a very simple thing to do. But, you know, if you could imagine coding that without using RxJava, it would actually require lots and lots of code. So it's a good demonstration of the power. So being told that I'm done, so it's sort of rather timely that here's my summary slide. So, you know, we've sort of come a long way. So I started talking of, well, we want to consume web services asynchronously in the front-end server. So that sort of pushed us in the direction of writing concurrent REST clients, and hopefully I've demonstrated that Futures are a great way of doing that. Netflix have gone down the path of using Rx Observables for that. So, you know, not only are they equivalent to Scala Futures, but they're also useful for processing potentially infinite streams of events. And there are people within the Android community who are actually using them for sort of Android app development as well. And there's actually a really good paper, if you go Google CACM Magazine, your mouse is your database, it actually talks about how you can use Rx Observables to simplify GUI code, because that's just responding to events. So they're this incredibly powerful unifying abstraction that's sort of useful across many different domains. So anyway, that's my talk. Thank you for listening, and I hope that you found it useful.
Let's take the questions downstairs here. There's a break now for coffee, a longer break. At 15:30, 3:30, the quickies are starting, and then we have the normal sessions back at 4. So.